this computer, admit somebody, and then go to a full slide mode. Hopefully this will work. Yeah. So if you remember, we were learning about various kinds of operators. I don't think we did this in the last two classes. We did it previous to that, but doesn't matter. Some amount of recap. So certain important operators that you should remember. One is essentially the, I think we can go back one more slide perhaps. Yeah, we should remember that there's something called as an identity operator. It may seem something which is rather trivial, but what you should remember is that it helps us. Just one second, let me get my spotlight. Yeah. So, what it helps us is to identify when things go to an identity. Okay. Yeah. So, it's a important thing to define this identity operator, and it essentially tells you that it leaves the wave function unchanged or the ket unchanged. Okay, so and if you can think about the matrix representation of an identity operator, it will be nothing but your identity matrix. Also very important, and this of course we kind of did in a bit of detail last time, which is essentially the product of two operators. Once again, I mean, you have all done whole bunch of, you have proved a whole bunch of relations of this which involve product of two operators. So I'm sure you're kind of clear with the idea now, and thank you very much for all those assignments. One more thing, I said it on the WhatsApp group, but I'll say it again. When you repeat and keep sending it to me, it is very difficult for me to look through because I have to give first priority to all those people who are sending in their assignment for the first time. So it is not always possible for me to look at the second round of assignments. And in fact, I have decided that I will not, for the simple reason that it causes a lot of fatigue to me. Okay, in the sense, I mean, it's very difficult for me to see so many assignments online on WhatsApp. Okay, so my eyes get horribly strained. So given that situation, I think I will look at everybody's assignment once. I will also discuss it in class. I will also put up solutions. If there is any confusion that exists at the end of 2 3 days, when you have, you know, listened to the discussion, you have looked at the solutions, you have discussed with all your classmates, then you can come back to me. But don't keep resending me the assignment simply because, not because it's not a good idea, it is of course a very good idea, but I will not be able to do it. Okay, so it's a limitation on my part, because you can imagine there are how many of you, 70 of you, one teacher. Okay, it is tough to look through 70. And what I realize is that I'm getting WhatsApp fatigue. Okay, I can't keep doing it. My eyes start burning, they start watering at the end of it. It's really difficult. So sometimes you may have found that I was taking time to get back on your assignments, and this is the reason. Okay, yeah. And remember, you are not the only group who's communicating with me. Okay, I have a lot of other messages which are work related, which I also have to attend to. Okay, so don't mind me. I will definitely look at your assignment the first time you send it, but I may not be able to do the corrections. Okay. So now, as I said, that it's very important for you to once again get reminded about what you mean when you say a product of two operators A, B. As I have told you before, it means B operates on the wave function first or on the ket first, and whatever is the resulting wave function or ket, A operates on that. And that is what you call as the operation AB. So please remember, whatever is on the left, on the rightmost side, gets precedence. That acts first and then the others follow. Okay, so similarly over here you can see when you write BA, obviously A is rightmost, and thereby that will act first, and then whatever is the resultant on that, B will act. And this of course we kind of talked about, that AB need not be equal to BA, and you define this thing which is called the commutator of A and B, which is denoted by this. Again, I found a few assignments where the comma was not clear. Please make sure your comma is clear. If you put it as a dot, it changes the meaning. Dot, as you know, can mean a dot product, and it can lead to enormous amounts of confusion even to yourself later on. Okay, so kindly take the effort and make that tail. Okay, a little long so that you know that's a comma. So it has to be square brackets again, square brackets please, and then the first operator comma the second operator. Okay. And this of course has the meaning of ab minus ba, and you realize that if the operations ab and ba were equivalent, then obviously this would go to 0, otherwise it is non-zero. Okay. So this and then of course you all proved these relations with the commutators. I'm not going to go further into that. So let me change my page, which I'm not able to do again. Oh, I don't know what keeps happening here. Okay, stop share and then share again. Right. So let me change page first. Okay, let's do resume slideshow. Okay. So then, of course, we talked about the inverse of an operator. And what is the inverse of an operator? An inverse of an operator. So given an operator A, if there exists an operator B such that B operating on A will give you the identity, then B is said to be an inverse of the operation of A. Okay. Now remember, the definition of an identity was required for this. Okay. That's why you needed to define something called as an identity operator, though at that point of time it may have seemed like a silly thing to do for you. All right. Because you will say, hey, it's doing nothing to the wave function, why do I need it? This is why you need it, so that you can define something which is called as an inverse of an operation. So if there is an operation, you take it back to the original state. Okay. So that's like an inverse operation. All right. So so Bay, as I said, is said to be the inverse of A. Now I haven't written it over here. You will find that an operator and its inverse always commute. Okay, it will always commute. All right. So ba will is equal to I also means that ab is equal to I. All right. Now let's then go to the operator which we define as an adjoint, and this is a little more complicated, and I realized suddenly over here that I hadn't put in some vital information, but I will add it. I will send these slides over to you at the end. Okay. Apart from everything else that I'm giving you, the lectures, I will definitely send this over to you as well. So this basically, please remember, if you are now have an operator A, let me get my annotate button once again. If you have, no, I don't want the pencil, I want the spotlight. Yeah. So if you have an operator represented by A, then its adjoint is represented by A. And I told you what this symbol is. It's called the dagger. Okay. So it is represented by A dagger. And how do you understand this A dagger? So essentially, if I write down an inner product like this between phi and A psi, then this will be equal to A dagger operating on phi comma psi. Okay. So this is how we define an A dagger. Or if you want to write it in the Dirac bracket notation, this is how you will write it. Phi inner product with A psi is equal to A dagger psi. That means the operator A dagger acting on phi and inner product with psi. Okay. Which can be actually written like this. I don't think I have explained this to you before. So this is like you can see it is written like this. There are three compartments to this whole business. The first you write phi A and then psi. Okay. And this, please remember, translates to either this, which means you can take the A and operate it on the phi, in which case the A goes to an A dagger, or if you want to do it with the A operating on the side, you keep it as it is. Okay. So this is how it works, and this is an important relation. Please keep it in your mind. So essentially, if you had a phi which was essentially operation A on, say, a chi, then these are the, as you can see, these are the ket notations. Then the equivalent bra vector notation would be like this. You would have the bra vector phi equal to basically A dagger acting on the bra vector chi. All right. So this is what you realize. Now, if you recall the definition of a Hermitian operator, If you remember, that was nothing but phi a psi inner product was equal to inner product a phi psi. So obviously, if you compare this and that definition of a Hermitian operator, you will realize that A is Hermitian when A is equal to A dagger. And how do you go from A to A dagger? Please remember, it's a transposed conjugate, right? If you are sitting in the matrix notation, what does transposed conjugate mean? It means that you change the rows into columns and you also change each element by its complex conjugate. Okay, I hope that is all clear. Now we also learnt about another kind of an operator, and this is a linear operator. This is a unitary operator. And what is a unitary operator? An operator is said to be unitary if its adjoint is also its inverse. Okay, so if you have an operator u such that u adjoint u dagger is equal to u inverse, then you will say u is unitary. And why am I telling you all this? Simply because it's extremely important, okay, to know about unitary operators. We are going to start looking at something called as unitary transformations after this, and you will realize that the unitary operators are vital. They are special operations, okay? So what should you remember about a unitary operators? Moment I tell you that an operator is unitary, you should realize that operator along with its adjoint, so u dagger, will be nothing but the identity. Okay, so u dagger is equal to identity is equal to u dagger u. All right. What else did we do last time on the commuting operators? We learned something called as compatibility. Okay. So please look at the word over here, compatible. Okay. So that's a very, very important word. And what does it essentially tell you? It tells you that if you have two operators, A and B, but these are not just operators, they are observables. Now, once again, let me repeat what are the properties of observables. They are linear. Please recall in your heads what it means for an operator to be linear. Secondly, is that they are Hermitian. Okay, remember all those things it means if they are Hermitian. And thirdly, is that they have a set of complete eigenfunctions. What does it mean to have complete eigenfunctions? So, the moment an operator is Hermitian, remember its eigenvalues will be all real and its eigenfunctions form an orthonormal set. Now, if these set of eigenfunctions are such that moment you pick up any state which describes any dynamical state of the system, okay, you pick up any wave function belonging to the vector space, you should be able to write it as a linear combination of these eigenfunctions. Then you say that this operator is an observable. Okay, so remember over here we are talking about two observables. Okay, and two observables, if they are such that the eigenfunction of one is always an eigenfunction of the other. So if you pick up an eigenfunction of A, it is definitely an eigenfunction of B. Similarly, if you pick up any eigenfunction of B, it is definitely an eigenfunction of A, and in which case you say that A and B are compatible. What did we learn in the last two classes, two sessions, I think? That compatible observables commute, which means that if you have a situation that you have two observables such that the eigenfunctions of one are always the eigenfunctions of the other, then they also commute. That means if you try to find out the commutator of these two operators, you will get a zero. Okay, so they commute with each other, which means the operation AB is completely equivalent to the operation BA. That was one thing that we proved. We also proved the converse. Please note that this is essentially the converse, right? This is the converse. And what is the converse? The converse is that if they commute, then they have a common set of eigenfunctions. Okay, so if A and B are commuting, then they are also compatible. So what have I written? If AB commutator is equal to 0, then every eigenfunction of A is also an eigenfunction of B and vice versa. Okay. Now, before we proceed, let me tell you these two statements which I kind of mentioned last time. Thus, when observables commute, it tells that simultaneous precise measurements of the variables associated with them is possible. Okay. It tells us that we can precisely measure the variables which are associated with those two operators. It is possible to simultaneously measure. All right. Now, this is a point which I didn't mention last time. This need not be limited to just two operators. You can have many more operators. So for instance, if you have a set of observables A, B, C, which all commute with each other, which means commutator of AB is 0, commutator of AC is 0, commutator of BC is 0, and so on and so forth, then there exists a complete set of common eigenfunctions for them. So remember, I have just extended it. Okay, we already knew it for 2, we have extended it to more. All right, so I think that is what I wanted to do in the recap. I'm going to stop the share and ask you whether you have any doubts in what we have done so far. Okay, do we have any doubts, please? Somebody has already started giving attendance. Do you want to leave already, Hashita, or go off to sleep or something? Huh? You have another class?
I'm sorry, ma'am. I'm sorry, ma'am.
No, 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 no. Don't apologize. It's good that you're being proactive, but I was just wondering why you were hurrying up so much. That's all. No issues. Yeah. Any doubts, please? Because we are just getting started now. Okay. We are just getting warmed up. Any doubts, please? Or has everybody gone off to sleep? Any doubts? I sound like what do you call it, a vendor at a railway station, who's like trying to sell things and nobody's listening to the poor person. Yeah. Hello. Are you here listening to me, or are you all asleep?
No,
Yes,
ma'am, we are
ma'am.
listening, ma'am.
Good, 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 good. Fine. Thank you. I think everybody's a bit down because of the lockdown news. I have to admit that I'm pretty depressed myself, but as I say, there's nothing we can do about it. Okay, so if you are all right with what we have learned so far, let us now move on to new ground. Okay, and what was this new ground that we talked about? I kind of mentioned last time, is that I seem to have raised a hand myself, or no? Okay, thank God. All right. So the new ground that we are going to be covering today is essentially to dealing with the uncertainty principle. So what have I told you now? That if two observables commute, then you can precisely measure the two variables. Okay, you can precisely measure at the same time. Simultaneously, you can do a precise measurement, right? So obviously, when you have the uncertainty principle come in, what do you all know? You know that position and momentum for a quantum particle cannot be measured simultaneously, right? So obviously, position and momentum do not undergo a commutation relation. Now, maybe with Meera madam, you have already seen that there is a special form to that commutation relation. So let me just write it down. So I will share screen now, but I will now go to my iScribe. Okay. So what you say, is this visible to everybody? Can
Yes,
everybody
ma'am.
see it? Okay, good.
Yes, ma'am.
Okay, thank you, thank you. All right. So what you might have already derived, okay, is the position momentum uncertainty principle. Yeah, what you might have shown is that essentially x and the momentum operator in the x direction, this is equal to I h cross. Okay, you may have already derived this. All right, so what we are going to do today is we are going to derive something which is called as the generalized uncertainty principle. Okay, this is what we are going to derive. And everything, all operators which follow the uncertainty principle will essentially come here. Now, please remember, commutation relations need not necessarily come up with, suppose it doesn't commute, it doesn't mean that it will always give you the commutator value of IH cross. These are special. Okay, these are special and these are linked to the uncertainty. The basically they will have an uncertainty relation. Okay, similarly, for instance, you know that, for instance, the E, energy operator, and time, okay, this will also have a relation like IH cross. Okay, so this is also there. All right, so now what is the uncertainty principle? All right, what is the generalized uncertainty principle? So before I go ahead, I will let you all know that I have picked this up from Quantum Mechanics, or Introduction to Quantum Mechanics by Griffiths, and I think I have the second edition, if I'm not mistaken. Okay, and this is on page 122. Okay, so those of you who have an access to this and you're confused by what I'm saying, even if you're not confused by what I'm saying, you can go and have a look there. All right, but this is where I've picked up the derivation from. So now, when I talk about uncertainty, okay, how do you actually define uncertainty? We have always been saying uncertainty in X multiplied by uncertainty in the momentum. Okay, uncertainty in X and uncertainty in Px should be greater than or equal to H cross by 2 or whatever. Okay, we've been saying such things, correct? Question is, how do you define an uncertainty? Now let me just tell you how it is
Ma'am, it
usually
is
defined. Yeah, is there any question? Does somebody want to answer that? Please go ahead.
ma'am, it is impossible to determine the simultaneously in the both of position and momentum, ma'am, in my microscopic particles, ma'am.
Correct. So that is the uncertainty principle, right? So what
Yes,
I'm
ma'am.
asking over here is that usually what do you say? You will say uncertainty in X multiplied by uncertainty in Px, that's the momentum in the X direction, is greater than or equal to some H cross by 2, right? So when
Yes,
I
ma'am.
call something uncertainty in X, what do I mean actually? How do I measure an uncertainty in a variable is what I'm asking. Okay. So do you have an answer for that? How do I measure it? I'm
Ma'am, it
saying
is
I'm obviously getting some number, right? I'm saying uncertainty in something multiplied by uncertainty in something else. If I'm multiplying, of course, I have a number. So can you tell me what is uncertainty? Just take a guess. You have actually calculated it in class, in the lab. So you've all done it. So you're not unfamiliar with it. Okay. Can you just tell me what do you think it is?
Error, ma'am.
Yes, absolutely right. It's the error. Okay. Yeah. But error in your lab is because of a human element. Okay. Because we have made mistakes, the instrument has made a mistake, the instrument has a least count, and so on and so forth. Okay. But in the case of quantum mechanics, this is inherent. Okay. You cannot be more certain than that. All right. So this is the difference between the two, but it is like an error. So how would you actually calculate an error? Let me say. So for instance, if you had a variable A, okay, what will you do? You will do measurements several times, right? Then you will get something which we call as an average value of A. I'm writing it in special terms over here. You realize this is an operator notation, and this is essentially what we call as the expectation value of the operator, right? Yeah. Okay, so in your lab, what would this be? This would be your average value, correct? Or your mean. You can also call it a mean, correct? And this is your measurement. All right. Now, what is your error? In the end, you will say, oh, I have to find out how good my whole experiment was. So I have to find out an error. How do you find out the error? Essentially, you will do A minus expectation value of A, correct? You will do this. But now there is a little bit of a problem. Okay, you, of course, every value you have measured 10 values, 10 of them will have different errors. Now what you realize also, that the errors can be positive, they can also be negative, correct? Now if I start adding them up, the positives will get cancelled with the negative, and in the end it will show a very small error, but that may not be correct at all, right? Suppose the value is 10. Okay, I should get a value of 10. Suppose I'm getting 30 sometimes and minus 20 sometimes. Okay, then I can add up and I can say, oh, I'm getting very little error. That's not true, right? You're getting actually massive error, because you should be getting 10, whereas you have been getting 30, or you're getting minus 20, or you're getting minus 10, or you're getting 40. Okay, so your errors are huge, but since they are fluctuating both to the negative and the positive side, they are nicely cancelling out, and you're feeling very happy. Oh, I have no error. That's not correct, right? So how do you do this? So the way you do this is that you remove this problem of this positive negative. Okay, so you square it. Okay, you square it, and then you take an average of that. Okay, you square it and take an average of that, and then you take a square root. Okay, so this will give you an idea of the error, and in our case we will call this uncertainty. Okay, I will write it as delta A. All right, so has everybody understood how we are getting the uncertainty? You need the expectation value, you need each and every value, you take the difference between the expected value and the value that you are getting. It can be positive, it can be negative. So each of these quantities you square. They are all positive now, no problems. Add them all up, take the mean, and then take the square root. Is everybody clear on this?
Yes, ma'am.
Okay, so now essentially I can say that delta A square is nothing but A minus expectation of A square, the expectation of the whole thing. Now remember, there is from statistics itself, there is an easier way of doing this, and in fact you will use that when you're doing the calculation. Here itself I'll write it down. Your delta A is also equal to what is this now? Expectation of A square minus expectation of A the whole square, the expectation of that. Okay, so this is okay, of square root. No, not the expectation. You will just put a just the square root of that. Okay, so I'm going to write this again. Okay, I'm writing this down again. This is nothing but your delta A is equal to A square expectation minus expectation of A whole square to the power of half. Okay, so it is always easier to do it in this way rather than do it like this calculation wise. Okay, you will find that once I give you some problems, maybe you will find that that is indeed the case. All right, now we will start working from this particular example. Okay, we will take this and we will try and get to the generalized uncertainty principle from there. Okay, so what we will do now, we are now going to have to talk about two observables, right? So one, let us call it A, and the other we will call it B. Okay, now remember that the uncertainty delta A, I'm going to also call it some sigma A, right? Okay, we'll call it sigma A. And then you have a delta B over here. I will also call it a sigma B. So what is this delta A? It's the uncertainty in A. What is delta B? It is the uncertainty in B. And similarly, sigma A is also uncertainty in A. Sigma B is uncertainty in B. Okay. Now, why am I doing this? Because Griffiths has used sigma A and sigma B. I'm just making the connection for you. Okay. That sometimes you will come across it as delta A. Remember, delta A is the uncertainty in A. Suppose somebody refers to it as a sigma A. Remember, that is also uncertainty in A. It's the same thing. Okay. So now, how will I? So let's start off here. Okay. From this equation over here, this one here. Okay. We will write it in terms of sigma A square is going to be equal to nothing but expectation value of A minus expectation value of A whole square, right? So this is what it is. Now, how do I write it down in terms of expectation values? We have done this before, okay? So we will say, remember this expectation value is always in terms of a, what is it? And with a wave function, right? So I will just write it over here. If you remember, expectation value of A is nothing but in the Dirac, in the, what do you call, in the uh, inner product expression, it was, we had written it down like this, if you remember, right? Yeah. Now let us assume that psi is normalized. If it is normalized, then what do we know? We know that psi comma psi must be equal to 1, right? So thereby expectation of A is nothing but psi A psi, right? Which we can write in Dirac bracket notation as psi A psi, or we can write it as psi A psi. Okay, I showed it to you today, right? So we will go for this notation here. So let's go here. So instead of just A over here, we have A minus expectation of A whole square, correct? So let us write it down. This can be written as psi A minus whole square psi. Any confusion with this? Has everybody understood how I wrote this down, this notation? No confusions, I hope. Any problems? Has everybody understood this step? What happened? I can't hear people.
Yes, ma'am. Understood, ma'am.
Okay, it's okay. Fine. Good. So now, then what can we do? We can write it as psi A minus expectation value of A minus expectation value of A psi. Okay. So from the square over here, okay, I've just written it once and then 2 times. Okay. Hope there is no problem with that. Now, we are talking about observables. They are Hermitian. So A is equal to A dagger. What about expectation value of A? It's just a number. Okay. So it is anyway that will be, I mean, we don't have to worry about it being Hermitian. It's a useless thing to ask. It's a number. All right. So what we will then be able to write, I will require a little space for this. That's why I'm writing it over here. This will be nothing but A minus expectation of A acting on psi inner product with A minus expectation value of A inner product of psi. Remember, if A was not Hermitian, this I'll have to put as its adjoint. But right now I don't have to bother because I know A is an observable and thereby A is equal to A dagger. Everybody okay with this? Yes?
Yes, ma'am.
Okay, so now let's go to the next step. I don't feel like writing this big thing all the time. So I'm going to write it a little differently. What I will do is I will define one new ket F. Can you see this? Yeah. So this is F, okay? Okay, I think I'll go to the next page. It's not good because I can see it, you cannot see it. Okay, I will also change the page here. All right. So we are now on the next page. So what we will do now is we are going to write down a ket F, okay, as equal to, what will we do over here? We will write it as A minus expectation value of A psi. Okay, this is F. Similarly, the equivalent bra vector, is going to be nothing but A minus expectation value of A psi. Okay. So now, if you remember, your delta A was what? Your not delta A square. Your delta A square, which was going to be equal to nothing but sigma A square. Did I write it like that earlier? Yeah, I did. Okay, thank God. Thought I'd made a mistake, which was nothing but A minus expectation value of A psi, A minus expectation value of A psi, okay, will now be written as F. Okay, it's nice, much nicer, much shorter, and I'm happy. Okay, so this is the idea. I could have done the whole thing with just A minus expectation value of A as operator, but it's a bit irritating, so I'm writing it like this. Okay, that is all. So now, similarly, I will write down this sigma B square, which will be, I'm going to write it down directly like this, will be nothing but B minus expectation value of B psi, B minus expectation value of B psi. Okay, this is what it was supposed to be. And here I will give it a special name. I will call it G. Okay. Okay, where G is nothing but B minus expectation value of B operating on psi, and the corresponding bra vector is nothing but this. Okay, so this is what we have written. So now let's go on and find out what is sigma A square into sigma B square. Why are we doing this, please? Finally, I'll have to prove something about uncertainty in A into uncertainty in B, right? Now, sigma A square into sigma B square is, of course, uncertainty into A of A in A multiplied by uncertainty in B whole square. Okay? But once I have this value, hopefully I can get somewhere. So this is going to be what? This is going to be nothing but any confusion so far, please? Is there any confusion? Because we'll get it clarified and then move on. Is there any confusion? All right. Yeah, just let me take a sip of water and then go on, because I don't want to stop after this. Okay, now let's think about what so let's just take a break over here, because I'm going to have to tell you something about something called as the Schwartz inequality. So let's just think about what this FF is. Okay, this is essentially equivalent, if you think about, to something like mod F square, right? Yeah, because what will this be? I have written it in a Dirac bracket notation, but nonetheless, this is nothing but this. Okay, because just let me remind you, FF is nothing but inner product of F with F, right? Which means it is nothing but summation of F star F d tau, which is nothing but mod F square. Okay, so please remember, this is like a magnitude square. Okay, so remember, we call this the norm. Okay, so it is like equivalent to a magnitude square. All right, similarly, so this is magnitude square of F in some sense. Similarly, if you write GG, it is equivalent to a magnitude square of G. It's a way of looking at it. Okay. So now what is this? So what we will do now is just think about in terms of vectors. All right. Okay. So we'll think in terms of vectors. So let us take two vectors. Okay. I'm going to change the page. Let us take two vectors. Let us say we take a vector C and a vector D. Okay. Now you know that the magnitude of C, okay, is essentially C dot C. This will be the length of vector C. Correct? Yeah. Similarly, you can do a D dot D. Okay. And this is going to be the length of vector D. Now, let us basically do a dot product. Okay. So inner product, please remember, is like a dot product. Okay. It tells you the projection of one mathematical function on another. Here, the dot product tells you the projection of one vector on another. Okay. So let's imagine we do C dot D. What is this? You know, this is nothing but magnitude of C into magnitude of D into, what is it? Cosine of the angle between C and D. Okay, so if this is C and this is D, this is theta, then this cos theta links to essentially this theta. Correct? Now, what you have to realize is that C dot D, okay, will always be less or at best equal to mod C mod D. Right? Does everybody agree with me? Does everybody agree with this argument? I'm waiting.
Yes, ma'am.
Why do you agree with it? Who said yes? Why do you agree with it? Why do you think it is correct?
Theta is very small.
Theta need not be very small, but what is the limit of the value of theta? Can you tell me?
Range
0
of
to 1,
Cos
ma'am.
theta. Sorry? Cos theta. What is the limit of the
1 to
value?
0, ma'am. Ma'am, in orthogonality, generosity property we'll use, na, ma'am.
Yeah, we use it in orthogonality, but what I am trying to tell you is that the cos theta value is limited between +1 and -1. Okay, it cannot be greater than 1. Correct? Yeah. So cos theta lies between -1 and +1. Correct? If it is -1 or +1, if it is -1, it doesn't matter. If it is plus, if it is negative, we will not bother too much. If it is positive also, the maximum value it can take is 1, in which case C dot D becomes equal to mod C into mod D. Okay, but it can never be greater. All right, so this is the important point. So now let us go back and put this whole idea on our, just one second, there's somebody who needs to be attend. Let's put this whole thing for our wave functions. And this is where we come to something called as the Schwartz inequality. It is essentially the same thing. And what does it tell you? It tells you that FFGG is always greater than equal to. Please remember this FFGG is equivalent to this. Okay? Is always greater than or equal to FG. This over here is equivalent to this. Okay? Of course, whole square. Yeah, I think you'll have to do a mod square of it. Mod square. Okay. All right. So basically, even if I take the projection of one thing on another, all right, and I take a square of it, over here, I will get it. So please remember, don't get confused by the square. Please remember dimensionally in this particular equation, this is like a length, this is like a length, and here you also have a length and a length, okay? But here to get it dimensionally the same, I have to take the projection square, okay, over here. Please remember that. Okay, there's somebody who's having a lot of trouble getting in. All right, so this is essentially your Schwartz inequality. I hope everybody has understood, okay, what the Schwartz inequality is, right? So now let's get back. What did we say? Sigma A square, sigma B square is equal to, and now what are we saying? That this is greater than or equal to, if we take the inner product between f and g, mod square, it's greater than that. All right. Now, let us move to something else now. Okay. So this is, so please remember when you write an answer, okay. So please pay attention. In the exam, you have been asked a question, okay, to write down the generalized uncertainty principle. All right. What should you do? Okay. So please note, you need to write maybe all this. Okay. You need to write down what is F. You need to write down sigma A square in terms of F, sigma B square in terms of G. Write down sigma A square into sigma B square over here. And then go directly where? Here. Okay. All this in between things which I am telling you is so that you understand what I'm saying. Okay. They don't have to be put in an exam. All right. You can just say, hey, I have this. Okay. I have this expression here. Right. And now from Schwartz inequality, I know that this and this is going to be greater than this. That is all. Okay. Please don't write all these in between things. They are all for your explanation. So now, once again, okay, let us go to the next step, and I'm going to give you some in between explanation which you don't need to write in the exams. Doesn't mean you don't pay attention. You should pay attention because it will help you understand. Okay. So what is this? Let us imagine we have a complex number z. Okay. So now z will be written as a plus ib. What is I? I is nothing but root of -1, right? What are a and b? A and b are real quantities. So a, b are real, and I is nothing but square root of -1, correct? So I hope you all remember this. Now, how do I write mod z square? That is going to be nothing but z into z star, right? What is z star? Z star is nothing but a minus ib. So this is of course going to be a plus ib into a minus ib. I'm just doing this for those who have kind of forgotten it a little bit. I'm sure most of you remember. Don't get angry with me for showing you all this. So this is going to be what? A into a is a square minus I ab plus I ba. But AB and BA, these are just real numbers. They will commute. Okay. And then you have minus I square B square. Okay. So let me write it down. Minus I square B square. Now remember, these two commute. No problems. So these two will cancel off. And then you will get A square. And then minus I square is nothing but -1. So you'll get plus B square. Correct? Yeah. So mod z square is equal to a square plus b square. Correct? And this, of course, is going to be larger than or equal to mod b square, just b square. Okay, everybody agrees with me? Everybody agrees with me that mod z square will be greater than or equal to b square. Is this correct? Come on, come on, wake up. Yes? Is this
Why not
correct?
a square, ma'am?
Yeah, everybody has understood this, right? Good. So now
Why,
yeah,
why not a square, ma'am?
why not?
A square.
Yeah, I have written b square only. You mean why not a square? Yeah, I could have written
Yes,
it
ma'am.
as greater than or equal to a square as well. Why I'm doing this, I'll tell you, is because I'm going to do a manipulation, and for that I need b square. Okay, I can do it with a square, but it's not going to help me. Remember why I'm doing this? I'm trying to solve this problem, from which I'm trying to get the uncertainty principle. Okay, so I have an agenda in mind, all right, for which this relation is important, the other is not. It's true. It's absolutely true that mod z square is also greater than or equal to a square. Absolutely correct. You're very much correct. But it's not going to help me too much. Okay? You understand? Lot of this,
Okay.
please remember,
Yes.
they are mathematical manipulations. I am picking up those tools which I need. Okay? The other tool, it may be true and it may be very good, but it's not going to help me right now. Okay? That is all. Nothing else. Is that okay? Not
Yes,
okay.
ma'am.
Okay, good. Fine. So let me now change my page. Okay, so everybody agrees with that, right? So how can I write this in other words? So let me try and write it down in this page itself. Okay, I can essentially write this down as, let me see if it works. Okay, I can essentially write this down as that mod z square is greater than or equal to imaginary part of z. Imz is imaginary part of z whole square. Okay, is everybody good with this? Instead of b now, b is the imaginary part of z, right? I'm writing mod z square is equal to imaginary part of z whole square. All right. Now, how do I get imaginary part of z? For this, I'm going to go on to the next page. Okay, so let me write down again. Just give me a second. Some of these pages are not sitting very well. That's because I've almost jumped all around over them, I think. Okay. Fine. Okay. All right. So your z, if you remember, was nothing but a plus ib. What is imaginary z? It is b. How do I get b in terms of z alone? What will I do? I will write z is equal to a plus ib. Z star is equal to a minus ib. Okay. All right. So if I do z minus z star, what will I get? I will get essentially 2ib. Everybody agrees with me? So this implies that b is equal to 1 upon 2i z minus z star. Okay. So imaginary z is equal to 1 upon 2i z minus z star. Right? So writing it again in that earlier things, what did we had? We had mod z square was greater than or equal to imaginary z the whole square. So now I can write mod z square is greater than or equal to 1 upon 2i z minus z star the whole square. Everybody with me? Yes, everybody has got this? There's nothing new really. You have done it in complex analysis in your BSc perhaps, right? But we will need this now. Everybody good? Yes,
Yes.
no, no ma'am, we are asleep, right?
Yes.
Okay, fine, fine, good. So now, what is the connection? Let us think about it. So we have, so sometimes when we do these derivations, we forget what we were trying. Sigma A square, sigma B square is nothing but F G G, which is greater than or equal to F G mod square. Okay, so this is the guy we are going to take in the place of mod z square. Okay, so therefore we can write mod F G square is greater than or equal to 1 upon 2i. Okay, and in this what will we get? Fg minus Fg star whole square. Everybody got this? Is this clear?
Yes, ma'am.
Okay. Now, what is Fg star? Please remember your inner product properties. What had we figured out? Phi psi is nothing but psi phi star. Convert that to your Dirac bracket notation, and this will be nothing but GF. Okay? Now, therefore, sigma A square, sigma B square is greater than or equal to mod F G square, which is greater than or equal to 1 by 2i F G minus G F whole square. Everybody with me? That whole square doesn't look very good. I hope it comes out properly. Okay, everybody with me? Has everybody understood this expression here? This one here.
Yes, ma'am.
Yes? Yes?
Yes, ma'am.
Any doubts whatsoever? Let's clarify it now. Okay? All right. So if you're good with this, let us try and find out what this FG is and what this GF is. Okay, so these are the two things we need to now find out. So first we will pick up FG. Let's go back a few pages. Okay, remember what FG is. Okay, so F, if you remember, we have written it right here at the top. It is this, correct? What is G? G is this. Equivalent bra vector for G is this. Okay, equivalent bra vector for F is this. Okay, so using that now we are going to calculate what is this. Where did we go? I think I went off one extra page. What is this FG, right? So I will write it down as A minus A dagger operating on F, and here I will write B minus B dagger, sorry, not B dagger, sorry, B expectation. I'm sorry. This is A expectation. This is B expectation. I don't know why I said dagger. I'm sorry. Okay. This is what we have, right? So what can we write this as now? We can write this as psi A minus expectation of A.
Expectation value of A.
Any doubts?
No, ma'am.
Feel free to ask, please. Okay, if I'm making some mistakes, absolutely stop me. All right, because sometimes I do stupid things, so that's why. Okay, let's open this up. I'm going to now multiply the central terms. I will have AB, okay, minus A expectation value of B minus expectation value of A, B plus expectation value of A, expectation value of B. Okay, now I'm going to separate the terms. So remember over here in the second term, your B expectation value of B is just a number. Okay, so I can take it out. So it will be here again, this is just a number. And the last one will be, I hope it will come over here, plus okay, this is what you get. Now, this over here, you will realize is nothing but expectation value of A. This what you have over here is nothing but expectation value of B. All right. So I'm going to go to the next page. I'm going to repeat the last step again so that you understand. So what do we have now? We have your F, G. I'm going to write down all the things again. You had psi, A, B, psi minus, what did we have? B, psi, A, psi, sorry. Okay. Minus A, and then lastly you had plus A, B, psi, psi. Okay. Now psi is normalized, so this will go to 1. All right. What is this over here? This is nothing but expectation value of A. What is this here? This is nothing but expectation value of B. What is this here? This is nothing but expectation value of AB. So what do we have over here? We have AB minus B expectation, A expectation, plus minus A expectation, B expectation, plus A expectation, B expectation. Now, since these are just numbers, expectation, this A, B, these are just numbers. Okay, even this is a number, don't worry. Okay, but that is not the same as the others. So we can just write your FG is equal to AB. Okay, then you will get 1 minus A. Okay, this is what you will get, because one of these, maybe this and this will just cancel out. All right, they are numbers, remember, you don't have to worry about commutations. Commutations is only between operators. Okay, so what's the time right now? Let me just see. Oh my goodness, I completely forgot. All right, so we'll take a break now. I'm absolutely sorry about this. We'll take a break, okay? And we will meet, I will really sorry for having taken up 10 minutes of your time. We will meet at 2:10, okay? I'm really sorry, all right? So we'll meet at 2:10 and we will continue with this. Is that okay? Really sorry about it. I somehow completely lost track of time. All right. So is that all right, everybody? I hope you have put in your attendance in the chat box. I'm going to stop the recording now. I will send you an invitation. We will meet at 2:10. I may send it to you at 2, but feel free to join by 2:10. By 2:10, please everybody join, and then we will continue with the class. Okay, fine. I'm going
Yes,
to
ma'am.
stop.